quickly talk over that. So pressure is in force per unit area. So for us, it would be newtons per square meter. But you could have inches of water, which is based on the working of this thing called a U-tube manometer, which was a very common pressure measuring device. If you leave it alone, the two levels of fluid in the two sides of the tube will get level. But if you put a pressure on one side, you'll push the fluid down one side, which means it goes to the other side. So that H is a measure of your pressure. And so you could measure it in inches of water, or if you wanted, millimeters of mercury, or whatever. So you can see how inches of water, centimeters of water, millimeters of mercury, inches of mercury. You can see how quickly you can get to many, many different temperatures, many different pressure scales. What's the pressure created by an 80 kilogram person balancing on a 4 millimeter by 4 millimeter heel? So here's the visualization. This is 4 times 10 to the minus 3 meters, and that there is 4 times 10 to the minus 3 meters, and we have 80 kilograms. So let's just do that. 80 kilograms. And I say, well, my force, my pressure is equal to force per unit area. And of course, my force is not my mass. That is equal to mg over A. So my pressure is equal to 80 times 10. And I've not given you the area. I gave you the length of side. And so we have over, well, it's going to be the length times the breadth, which is 4 times 10 to the minus 3 over 4 times 10 to the minus 3. So pressure is equal to 800 over 4. 10 to the minus, over 16, I'm sorry. 800 over 16 times 10 to the minus 6. So my pressure is equal to, well, that goes into that 200 times, and that goes into that 4 times, and that goes into that 50 times, if I did that right. So that would be 50 times 10 to the plus 6, because it was on the bottom, now it goes on top. So pressure is equal to 50, if you like, you can call it megapascal. That's a tremendous amount of pressure. An atmosphere is 100,000 Pascal. 10 of those would make 1 megapascal. 500 atmospheres, that's the pressure. And the reason why this comes to my mind anyway is that my mom was basically 5 foot tall, 4'10", something like that. And I don't think, apart from when she was like just walking around the house, I don't think I ever saw her without stiletto heels. There were small stiletto heels. They weren't the high stiletto heels. They weren't dress shoes. They were like working shoes, but it was like, they kind of looked like that. But they had a stiletto heel on the bottom. They had a little metal tab on the bottom. And the reason for that, frankly, was that they lasted a long time. They were like, you know, the metal didn't wear out. So she could wear those, and, you know, she wore those. She went to work in them, she went shopping in them, all that kind of stuff. And one day, she steps on my big toe in the kitchen, and she nearly broke, right in the joint between the two toes. And I jumped up, and, oh, man. And she kind of laughed, and she was very apologetic. And she said, and this always stuck with me, she goes, oh, yeah, stiletto heels. She goes, they're a woman's best friend. And I said, what do you mean? She goes, when I'm on the bus and it's really crowded, if people get a bit too close to me, because you stand in buses, you sit when there's a seat, but you stand when there's a stand. She goes, somebody gets too close to me, I just lean back I just put my heel on his toe, and he moves real quick. So, which I thought was really kind of good, you know. So anyway, and then in my school, they had a brand new school. In Britain, they don't have auditorium. Well, in my day, they didn't have auditoriums. They had a hall. And that hall would have a stage at one end, and it could be used for concerts. It could be used for, assemblies when the headmaster kind of like tells everybody off because they did something wrong. It could be used for dances. Check all the chairs out. And it's a dance. Put chairs in. It's a concert hall. Whatever you want. It could be used for. You could do PE in there during the day when it's raining and all that kind of stuff. You could do that. And it was oak floored. It was really, big area, oak floored. And so what they did was they gave, and parents' evening. So parents' evening in Britain, I think, is different than most people's parents' evening. Certainly my experience in an American school. When I taught in an American school, I sat in my classroom, and parents would wait outside and then come in and see me, yeah? And in Britain, they put all the teachers on desks around the outside of the room. And all the parents come in, and they congregate in the middle, and then as they see, you got to see me. Parents come, and when there's a break in front of me, they come and see me. So I just sit there, and I'm looking at the parents, and they're coming to see me. And you speak quietly, because it's confidential. It's not that confidential in Britain. In my day, it wasn't that confidential. And there was a double-edged sword to that. One was in one room you could see, I got to see that person, that person, that person, that person. So you weren't outside a room when somebody was talking forever. You could go somewhere else. So it was like really convenient for the parents. And it was also really convenient for the teachers, because parents' evening was not just about parents coming to see teachers. Parents' evening was also about teachers going to see parents. So I remember in my first year teaching, my chair of department, she said to me, "You've been having trouble with Jennifer Smith." Yeah, well, yeah. Okay, tonight you get hold of her mom and you give her a good talking to. And so I sat there and I don't know what Jennifer Smith's mom looks like. Oh yeah, she looks just like Jennifer Smith. It's amazing. Quite often they look very much like their parents. And so I had a chat with her and said, hey, I'm really unhappy because of this, this, and this. And it sorted the problem out. It was so nice, So they wanted to keep those floors nice and nice. They didn't want mom walking across them with 50 megapascal pressure on those floorboards, because they would then be indented. So they'd have these little, if that was your heel, they'd have this little kind of like plastic cover, which basically just spread out the area, to kind of like 1 inch by 1 inch. And no problem with the floors. Really clever design. So anyway, so pressure. What pressure is exerted by a right cylinder, right meaning 90 degrees, between the base and the sides, of radius 2 meters and height 4 meters, and density, we're beginning density now. Density equals 8 kilograms per meter cubed. So, all right, so I can make a list. Density equals 8 kilograms per meter cubed. That's good. And my H is equal to 4 meters. And my R is equal to 2 meters. And what do I want to know? I want to know pressure at the bottom. So P equals, my pressure is equal to my force per unit area. And my pressure, my force will be my mass times G. And my area will be pi r squared. But you know what? I'm not given the mass, am I? Oh man. So that means I got to take the density times the volume. Can you see that? If it's so many kilograms per cubic meter, if I work out how many cubic meters I have, I know the number of kilograms, yeah? So that would be density times volume times G over pi r squared. And of course, let's go down here. Density times volume times G times pi r squared. And of course, my density is my density, but my volume is pi r squared times h. That's my volume, yeah? Right cylinder, area at the bottom times the vertical height. Times g over pi r squared. Oh, that's nice if you think about it, because good old pi r squared goes away. That's interesting. So my pressure, let's try and make our pressures, this is shame on me. I should be drawing these very differently, because my pressure is not the same as my density. And sometimes, as I write them, they look like the same. So my pressure equals my density times G times H. And so that's going to be my density, which is 8 times 10 times 4. So pressure is equal to 4/8, 3 to 24, 4/8 to 32, 320 Pascal. Can you see how, because I'm working in sentences, because I say something equals something, the fact that I can't plug my numbers in straight away is not a big deal, because then I say, okay, I don't know my force, oh, it's mg. Oh, I don't know my mass, oh, it's rho v. I can keep on working. So, and I don't lose track, whereas I'm still seeing, and I really want to encourage you, if you're doing this, to just stop it. I'm still seeing people putting phrases down. They'll put mg over here, and they can't figure it out because there's no m. And they're kind of like, pi r squared over here, over there. They can't figure out the volume because there's no h. It's almost like they're remembering phrases of things and hoping that in their mind they can put them together and work out the answer. And that works for simple stuff. But for this, which is not really that complicated, it's just like several steps to it, it doesn't help you at all. But if you say, what do I know? I know pressure equals force times area. Oh, I can't do that. One of these guys has to be broken down into something else. Oh, well, force is equal to mg. It kind of guides you through it. And so I'm not using this intuition. I'm not trying to do stuff in my head. I'm just like saying, this is what I know. I'm going to change things until I get it where I can put numbers in. And then I put numbers in. You know, so for instance, in this question, I could, if I chose to, not give you the radius. Just not mention it. And then, you know, if you're not careful, you go, well, I can't possibly do this because I can't work out the volume because you didn't give me the radius. Well, yeah, but, you know, and I'll turn around and say, everything you need is there. And, oh, man, you can't work out the volume, so you can't do it. But if you put it inside the equation, it cancels out. And all this is like physics world or engineering worlds trying to make it so that if you think in sentences with equal signs and you do substitutions, you get rewarded. And if you don't, if you're thinking about this bit over there and that bit over there, you won't be rewarded. You'll be so, man, I can't do this. Oh, I need to do it this way. Because this way makes you much more powerful. So really, if you're doing a bit over here and a bit over there and a bit over there, then just really recognize that you'll get away with it a lot of the time. But man, there'll be times when you don't get away with it because you've got to be able to do that logical sequence like that. And it makes life easier. To be honest, it makes life so much easier because you can just see it unfolding. And you know, it's like, yeah, when you first begin, it's kind of like it's a challenge. There's no question about it. But this is the way to get stronger and face the challenge. It's by thinking in sentences, and that's what I see sometimes. Consider a shape-shifting object that can change its footprint area, but not its mass. A student calculates the pressure that an object exerts on the floor for different footprints. So I might have that, and I might have that, and I might have that. And same amount of stuff, just redistributed in different ways. What should a graph of pressure, so that's my pressure, versus area, there's my area, look like? And I say pressure is equal to force per area. and my force is equal to mg times area. So, as my, well, m's a constant. Consider a shape-shifting object that can change its footprint but not its mass. So m's a constant. It stays on the Earth, so g's a constant. So I can say that's mg, there's my little constant, times 1 over a. And if you look at that, can you see what the relationship between P and A would be? What's the name for it when it's something is equal to a constant times 1 over something? Inverse, isn't it? You can see it. And so for many people who go inverse and, well, what do I do now? The easiest thing when you want numbers, this is the next stage. I could just as easily have given you the old PA and gone and done that, and that. Remember that? You've seen that in tests. I could well do that. But in Physics 2, I'd like you to be able to do much more of this where you actually plot things out for yourself. And so for that, what do you do now? Well, you're going to do a P and you're going to do an A. And you're going to go A is 0, 1, 2, 3, 4. So if you like 0, 1, 2, 3, 4. And I don't know, let the mg equals 1. So then this P is 1 over 0, which is infinite. And then it's 1 over 1, which is 1. So let's go 2, 4, 6, 8, 10. Let's call that 1. And then it's 1 over 2, which is like a half, which is there. And then forget about 1 over 3. Well, I can do 1 over 3. 1 over 3 is going to be like a third, which is like 33, which is there. And then 1 over 4 is easy. 1 over 4 is a quarter, which is like there. And 1 over 5 would be 0.2. So I'd like you to get to the stage where you can make up your own numbers and it doesn't faze you. I know to begin with, at this stage, you'd be like, oh man, where do I begin? But just get used to the idea that, I could have said 16 for my P and gone from 16 downwards. The shape is what matters, not the absolute numbers that you use. Once I define that first point, whether it's equal to 1 or equal to 16, if I chose to call that 16, then I would have basically, for this one down here, would have been 4. So. Cool. Let's have a look. I'm a bit behind, so I'm going to just float on. Imagine a jar of water. If you imagine going deeper in the water, well, imagine that you're in a silo, or imagine you're in a closet and you go to sleep, just like a party, and you just go to sleep. And people decide it'd be fun to just put bowling balls on top of you. So they carefully put a layer of bowling balls on top of you. You might not even wake up. But then they put another layer on top of that, then another layer on top of that, then another layer on top of that. Pretty soon you can get squashed, yeah? We know that. You can't have an infinite number of bowling balls above us. We're going to get squashed. But we have a fair amount of air above us. We have 50 miles of air above us. Thing is, it's dense down here, but not dense up there. So the top reaches don't add much weight per square area, force per unit area. But it adds up. We just don't feel it because we're pushing out as hard as it's pushing in. So we don't feel it so much. But even if you have a glass of water, then what happens? The pressure under the surface is not the same as the pressure at the bottom. And water is quite dense, so it's going to be a measurable difference. And so we have a few bits of terminology now. It's only terminology, really. The pressure here, let's call that absolute pressure. Because I want the total amount. And the pressure that's the absolute pressure is, well, there's going to be a pressure caused by the atmosphere. So I've got to take that into account. So there's my pressure of my atmosphere. And then we have what's called a gauge pressure. And the reason why it's called a gauge pressure is because back here in the day, that was your pressure gauge. And so they got used to saying, oh yeah, the pressure caused by the column of liquid is your gauge pressure. You know, that's how they got to it. And our gauge pressure is rho times G times H, the density times G times H. And actually, if you think back, that was just here, wasn't it? Rho GH. We figured that bit out anyway. Okay, so I could ask you what the gauge pressure is here, P gauge, in which case you ignore the atmosphere, or I could ask you what the absolute pressure is there, in which case you've got to take into account the atmosphere. Why would you ignore the atmosphere? Because I could actually put this inside a glass cylinder and take all the air away, in which case I don't have to worry about the gas inside because it's all gone. So there is no atmospheric pressure. I could do that. And in fact, that's a barometer. That's how a barometer works. So there's a reason why they have these three terms. And they're not hard. It's just your atmospheric pressure is your atmospheric pressure in Pascal. Your gauge pressure is your pressure of your liquid. And that's going to be the density of the liquid times G times the height of the liquid column. And you add them together if you want the absolute. It's as simple as that. So a barrel is filled with a fluid that has a density of, so my density equals 4 kilograms per meter cubed. And the barrel is open to the atmosphere. And the atmosphere, PATM, is equal to 80 Pascal, a really small atmosphere. What is the absolute pressure? PABS. And my height, H, equals 3 meters below the surface. So I'm here. This is 3 meters. This is the density of my fluid. I have my PATM, and I want my PABS. So I say my PABS is equal to my PATM plus P gauge. Every time I write it down, it gets a little bit more reinforced. That's how you learn things. PATM plus rho GH. PATM is equal to 80. ABS, I'm sorry, I said ATM and I wrote ATM. It's ABS. P absolute is equal to 80 plus my density, which is 4, times 10 times 3. So P absolute is equal to 80 plus 120. So P ABS is equal to 200 Pascal. I'm not above giving you that exam question, but asking you for the gauge pressure. Why not? It tests your conceptual understanding. Do you know the difference between the absolute pressure and the gauge pressure? But sometimes I think that people, they kind of go into auto mode and they answer the wrong question. And as a teacher, I can't tell, is it just that they misread it, or is it that they have no idea what, they only know what they know, and they just learn this one problem, and whatever I ask on this topic, they're going to give me this solution, because the only thing they learned. So it makes it very hard for me to give credit when it's completely the wrong answer it's the right answer for the completely the wrong thing. I worked in high school for a year, for 4 years, and I had this one group of young men who actually went on to become lawyers and engineers, actually, that's what they became, who were just like, man, they just made an art form out of cheating. And at the very end, on graduation night, when everybody was like talking, I had a chat with them, because I knew they were cheating in chemistry, and I could not find out what they did. And they started just bragging about all the different ways, and it really opened my eyes as a teacher about, oh man, like the old thing about, if you think it's one of two answers, but you don't know which one it is, you put them both down. And teachers will tend to, as they look, they'll see the right answer, and they'll check it off. And they'll kind of ignore this stuff over there because it's not the right answer. And if that's the right answer, they'll check that off and ignore that stuff. So they're deliberately putting down two answers. And it's like, man, that would never have crossed my mind, you know? So I'm a bit jaundiced as I go after that experience. I got a bit jaundiced about, hold on, so you mean to say when you put down that completely wrong question, you answer a completely wrong question, it's because you had no idea what to do otherwise? You didn't just misread it? Yeah. So watch out. I've got some students that they use a highlighter. And they highlight, so they say, this is what he wants. You know, in orange, he wants this. Because they answer the wrong question sometimes. Because they recognize, you know, the diagram or whatever. So watch out for that. Sometimes when I give what I think of as the easier question, the solutions are not. People are just set up. Case in point, your collision was not elastic. It was perfectly inelastic. It said perfectly inelastic. It talks about the two masses combining. I can't tell you how many elastic collisions I had. It's like, because you can't. I know he's going to give an elastic collision. And I gave you a perfectly inelastic because I thought the test was a bit long. So I thought, I'll just make it a bit easier. I'll just give them and they'll kill it. And it's like, it's not like that. So watch out for that. Just watch out for that. Open tube manometer. So basically, this is a U-tube, sometimes called a U-tube. There's atmosphere here. And this is what you're wanting to test. And so if this is a higher pressure than atmosphere, you get this imbalance. And, you know, it's not just the pressure of the fluid that's balancing the pressure. Think of it like a seesaw. It's not just the pressure of fluid on the right-hand side that's balancing that test pressure. It's also the atmosphere above the fluid. And so the problem with these things is that if you have a high-pressure weather system coming through, then you'll get less of a fluid column because you don't need as much fluid to balance the test pressure. And if you have a low pressure coming through, then you'll need more of the fluid to balance it because it's the combination that balance this test pressure. So it's not such a good gauge, but it's kind of useful. And again, test pressure is equal to atmospheric pressure plus gauge pressure. It's like this guy. It's just rearranged rather than having the fluid. You know, you're making that liquid and you're kind of making that liquid into two and you're messing with it. Like that. So open tube manometer. And then, most places, in fact, I'm thinking about trying to get them to get one for us because they're not that bad. They used to be filled with mercury because it made them quite compact, and these days you couldn't get away with it. It's like you can't have mercury in a place of work or a school. What does mercury do if you breathe in the vapors of mercury? Any idea what it does? What does it cause? Causes it affects your mental capabilities, your thinking. If you read Alice in Wonderland, you know Alice in Wonderland, Alice Through the Looking Glass, I guess it is, yeah. The Mad Hatter. It's like, you know, we know it as just a thing, you know, the Mad Hatter. It was a stereotype of its day because hatters at the time, felt hats were, everybody wore a felt hat. Men wore felt hats, women wore felt hats. They were very fashionable. And to clean felt, you can't just get a brush and scrub it because it will show the scuff marks. It's very delicate. And so they wanted a way of cleaning the dirt off it by a vapor technique. And they didn't have the solvents like they have now. They had mercury. And so they'd have a tub of mercury, metal, and they'd heat it so that the mercury vapor would come up. The mercury vapor would come up. It would attach itself, you know, just the way chemicals do, attach itself to this grease and dirt, and then it would, you know, ease it off and then sink back down. So it's doing just what a dry cleaning system does. Can you imagine working most of your adult life in a place, in a room, with all these hats? And it would just, they'd go loopy. They'd have problems earlier in life than most people do. And so they talked about Mad Hatters. For children, developing children, it's really problematic, you know. So you wouldn't have a mercury-filled one, you'd have a water-filled one, and, you know. This is the alternative. And the alternative is that you basically seal off this air side and you suck the air out. So basically you have a vacuum, no pressure. And that makes it simpler because now you test, and I got to, so there's a bit of an issue here in terminology. That P atmosphere is what I'm trying to find out. So really that P atmosphere is what I want. Whereas here the P test is what I want. And can you see how, you know, the P atmosphere on this side, on the left-hand side, is something I've got to take into account, but it's not what I'm trying to find. The atmosphere on the right-hand side is what I'm trying to find. And so I could call that P test. It happens to be the atmospheric pressure, but it could be P test. I could have this. Where that's a vacuum. And that's test, P test. And what you'd say is, oh, P test is equal to, well, that's going to be 0. P gauge, yeah? Because there's no atmosphere here. There's only, you know, an empty space. Make sense? So watch out for that being P atmosphere. It's not forming the same function that P atmosphere does. This is what you want to find out. And so in this case, P atmosphere is equal to just the gauge pressure. And pretty well, you know, when people couldn't think of a present to buy a family member, like I can't tell you how many little barometers we had in our house as a kid growing up. People would buy them that have, you know, memories of Skegness. And it'd be a little thermometer and a little barometer. And it'd be like you put it on your wall, and it's a way of advertising for the town, a holiday resort, you know. And many of them were filled with mercury, and that's not good. They're kicking around. At USF, they had a whole bunch of barometers. When I took over the labs there were a whole bunch of barometers. We weren't using them. We were in the stock room, and basically I had to get waste disposal to come and take them away, because it was hazardous waste. And they'd been kicking around. You know, how many of them had broken during the 60 years or so before we started, and were kind of like in the skirting boards and stuff like that. It's mercury's a funny stuff. So open tube manometer is filled with a fluid that has a density of 6. So the density equals 6 kilograms per cubic meter. A cylinder of compressed gas is connected to the one end of the tube, and it causes a height difference. My H is equal to 4 meters, and my P atmosphere is equal to 300 Pascal. And what's P test? So I'm going to say, well, okay, here's my P test. We'll do it like that. That's like that. So there's my H, and here's my P ATM. It's my P test. There's my P gauge. So P test is equal to P atmosphere plus P gauge. P test is equal to P atmosphere plus rho GH. P test is equal to 300 plus 6 times 10 times 4. So same old, we've done this before. P test is equal to 300 plus 240 P test is equal to 540 Pascal. So we just go through and we'll see that thing going. Okay. Barometer is filled with fluid. Okay, so let's draw the barometer. It tends to be drawn symmetrically, it doesn't have to be. Filled with fluid, and the density is equal to 8 kilograms per cubic meter. And pressure causes a H. H is equal to 5 meter tall column of fluid above the reservoir. And this is vacuum. That's what makes it a barometer. So I can say, if you like, I could say P test is equal to P atmosphere plus P gauge, where the atmosphere is there and that equals 0, just like we did the last one. Or we can recognize, for a barometer, then we say P atmosphere is equal to P gauge. And I don't know which way you prefer. Do you prefer the general solution, recognizing that this is a special case which has an atmosphere of 0? Or do you prefer remembering, this is the equation for a barometer? But P atmosphere is equal to rho GH, which equals, in this case, 8 by 10 by 5, which equals 400 Pascal. Yeah. And it's like, barometers are typically used to measure pressure, measure atmospheric pressure. So no, this is the atmosphere. The atmosphere is here. That's the problem. So what do you call the atmosphere? Do you call the atmosphere this bit, which it is, or do you call the atmosphere the bit that's above the fluid, which is 0? So it's like a real problem in terms of terminology. It's like, and it's not that somebody was crazy. It's just that you got these two areas, and then in the textbook they put side by side.
And you teach, and basically the atmosphere would be the test.
So
if you did it that way.
Yes.
Right.
So it's like, man. So, and I'll tell you, when you're brought up in the disadvantage that you guys have, and I'm very respectful of it, the disadvantage that you guys have is that all this stuff comes so quickly. I would have done this kind of like a week apart, and I'd have done it a few times before I got to this level. So what seems obvious when you just lived with something for a while, and you don't even see the conflict, when you look at it afresh and you look at it side by side on the page, you go, well, that atmosphere is not the same as that atmosphere. But they're both called atmosphere, So that's the problem you have, is you don't have time to live with it, to kind of like just separate. Change. This is, you go to the shop and they lift your car up in the air. Have you ever wondered how they can do it? They're just like, it just goes up like that. And there's all these tubes, and they're using hydraulics. And hydraulics are great because, like a piece of string can take a force around a curve, not many things will take a force around a curve, but a string kind of will take a force around the curve very nicely. Most things cause levers, but a string just circles around. Well, so do fluids if you put them in a tube. So we have two cylinders, a narrow cylinder and a wide cylinder. They don't have to be circular, but usually they are. And we connect them by a tube, and we put a piston in the top and a piston in the top. And these pistons can go up and down. These pistons can ride up and down. So they're free to, they just ride on top of the fluid. And I can describe to you what happens in terms of volume. You can turn around and say, well, hold on. If I push down on this little piston, then I'm going to basically push this fluid out of the way. And the fluid has to go somewhere, so it's going to go into this piston, and it's going to occupy more space. So that piston is going to go up. Now, because this is a narrow piston, which means a small area, if I push it a certain distance, I'm not going to get that same vertical height. I'm going to get only a small height, but it is going to rise. So I can talk about it in terms of that. I can also talk about it in terms of pressure. And Pascal's principle says the pressure, consider a system consisting of two cylinders of different cross-sectional areas. The cylinders are connected together. The system is in equilibrium. That means it's balanced. Pascal's law states that a change in the pressure applied to a fluid is transmitted to every point of the fluid and the walls of the container. So as a consequence, the pressure there is exactly the same as the pressure there. Now that means, so if the pressure 1 equals pressure 2, that means the force at 1 divided by the area of 1 equals the force at 2 divided by the area at 2, because that's what pressure is. And if I show it a bit more graphically, a little force over a little area can balance a big force over a big area. Now that's very valuable. So I can have my car sitting on the big piston, and I can have my thumb on the little piston, and I can balance them. My thumb can push on the little piston with just the right force to balance all the weight of my car on the big piston. And not only that, if I want to, I can even squish my thumb down and push the car up. Not much, got to push down, tiny little rise, but I can rise it and lower it. And that's what hydraulics is all about. Little forces applied to little area pistons, producing big forces applied to big area pistons. And it seems like you're getting something for nothing. You know, little force, big force. Whoa, you know, where's that coming from? It's coming from the little force to get actual work out of it, to actually lift things, not just balance things, but to lift things. That little force has to go through a big distance, which means a lot of work to get a big force going through a little distance, which is a lot of work, but it's like, you know, it balances out. So a typical question would be: a hydraulic system consists of one cylinder that has a cross-sectional area. So let's do that. I never show which one's big and which one's small. So, and that's going to be 4 square meters. It's connected to another cylinder that has an area. Oh, it is bigger. Okay. So that's going to be like that. That's going to be 12 square meters. And a force of 9 newtons. And what force acts on this guy? So that is F newtons. So I'll say, well, Pascal's principle, P1 equals P2. And I should, I suppose, draw the piston in, but I tend not to bother with it. But, you know, you get the idea. There's my piston. So F1 over A1 equals F2 over A2. So 9 over 4 is equal to Fn over 12. So Fn is equal to 9 times 12 over 4, which equals 27 newtons. It's a 3-to-1 ratio because the area is of a 3-to-1 ratio. How could I make this question a bit more interesting as your teacher? How can I make it so you've got to work a little bit harder? All right, what can I do?
The dimensions of the cylinder.
Yeah, I could give you the radius, couldn't I? Yeah? I could give you the radius, in which case it would be F over pi R1 squared is equal to F2 over pi R2 squared. Yeah?
Will give us the density of the fluid.
Oh, no, so the density of the fluid is irrelevant, actually.
Wait, but does pi r squared cancel and it basically?
No, the R's won't cancel because they're going to be different R's. Yeah, the R's won't cancel. Yeah. okay? But it's squared. That's going to be the catch, it's squared. And the other thing I could do is I could not tell you the force, I could tell you what mass I put there. So I could go m1g over pi r1 squared is equal to, I could ask you for m2g over pi r2 squared. I could say, what mass can I put on the other side? Or I could turn around and say, what force is it? Give you a mass on one side and a force on the other. Man, you know, mass on one side, force on the other. Man, that's not a force. What do I do to make it into a force? Oh, mg. You know it. It's just, can you bring it to mind? Can you spot it? Oh, he's given me mass. He didn't give me the weight. He gave me the mass. No problem. I can get the weight from there. So put yourself in my shoes. Just, you know, what games would you play with me? I don't want to make the homework like so involved that you can't make your way through it. So I tend to make the homework kind of like straight ahead, you know. Practice this. It's like going to the gym and just doing reps. But the tests, they are a little bit more. It's more like where you're playing a game and you're challenged a little bit. So you challenge yourself. Look at the old questions, but they're not all. I've not gone through all the questions I can ask. So look at the old tests, but don't just ask yourself, how could I make this more interesting? You know? And it would be good exercise. It's good exercise. Okay. So let's talk about fluids and floating. So this is buoyancy. There's two possibilities. Either you're floating or you're not. And we distinguish between the two. And we're going to start off with not. Now, maybe you're not because I'm holding you below the surface. Or maybe you're not because your natural state is to be below the surface because of your density. But on any object that's immersed in a fluid, there are two forces that I can consider acting on it. There's its weight, and there's what's called a buoyant force. And if this thing is happily under the surface, not accelerating upwards, not accelerating downwards, I'm not holding it down. If it's happily under the surface, then it's in equilibrium, yeah? So I need to be able to look at a situation and figure out what the weight of the object is and what the buoyant force of the object is. And we've kind of seen this before. The weight of the object, well, Fg is equal to mg, but I can define my m in terms of my density times my volume times g. Agreed? 4 kilograms per cubic meter times 5 cubic meters is 20 kilograms, yeah? So, okay, so get used to that. And what we typically say is rho GV. Why that order? Because it's just, you know, it's just the way it is. This is about an object. So we'll call it the density of the object and the volume of the object. G is just the acceleration, just the gravitational field strength on Earth. So it's a little bit of an unusual form, but it's going to be used a lot in this section. It's just mg expressed as a density and a volume. And we want to talk about densities because we're going to compare the density of the object with the density of the fluid. It's going to be useful. The buoyant force. And the problem with FB is it could be F block. So maybe it's best to put BOUY just so that we don't get those two confused. The buoyant force. Now the buoyant force, if you think about it, this fluid used to be down here. And then we put the block in it and that fluid was pushed higher. That's displaced fluid. It doesn't want to be higher. It's been displaced. We did work in either, well, did we do work? Let's not talk about that. But that water does not want to be on the surface. So, okay, it's going to try and push the block out. And so this is going to be about the density of the fluid times G times the volume of the displaced fluid. So the little mantra, the thing that you can get confused about, that I want you to not get confused about, is the weight is all about the object. And the dense and the buoyant force is all about the fluid. We say that floaty has buoyancy. You can say that floaty has a buoyant force, but the buoyant force is all about the fluid that the float is in. It's really about the fluid. It's not about the thing itself. The weight is about the thing itself. And the interesting thing is when you are submerged, what can you tell me about the volume of the object and the volume of the displaced fluid? They're the same. V object equals V displaced fluid, because it's under the water. Yeah. It's the same. That volume is the volume of the object, and oh look, that's what's pushing the fluid higher. So it's also the volume of the displaced fluid. Here, the volume of the object is not the same as the volume of the displaced fluid. So when you're floating, that's not true. But when you're submerged, that's true. Okay? This is a conceptual question. Picture throwing a cubic meter of lead. Yeah, if you've been working out, you can do this. So a cubic meter of lead, PB, into a swimming pool. Now picture throwing a cubic meter of, styrofoam is the stuff they make the cups out of that you drink out of, yeah, styrofoam. I'm giving it away with a diagram, but, Which has the bigger buoyant force? So, I want you to decide, is it the lead or is it the styro? And then I want you to tell your partner. Which is it? Which has the bigger buoyant force? Look back at the definition of buoyancy. Which has the bigger buoyant force? Not which one has the bigger buoyancy, not the same question. It's the buoyant force. Which has the bigger buoyant force? And I'm going to tell you the answer, and I want somebody who agrees with it to tell me why. And the answer is the lead. So anybody who will care to tell me why is the lead the bigger buoyant force? Because, F boy is equal to the density of the fluid, same fluid in both cases, times G, same earth in both cases, times the volume of the displaced fluid, and that's displacing all that fluid, and that's displacing that amount of fluid. Now, whoa, but one floats and the other one doesn't. Yeah, this is the buoyant force, F, B, U, or Y, and there's the weight, F, W. And this is the buoyant force, F, B, U, or Y, and this is the weight, F, W. This is FG, sorry. This floats because it's a tiny weight balanced by a tiny buoyant force. And this does not float because it's a massive weight. And it can't produce, even when it's completely submerged, enough buoyant force for it to actually float. So ironically, the lead has the bigger buoyant force. I'm not talking about buoyancy. I've not mentioned buoyancy apart from to say I'm not talking about it. Okay, I'm not talking about buoyancy because that's an overall effect. That's a net effect. And yeah, the styrofoam has a more buoyancy than the lead does, but I'm not talking about buoyancy because I don't have an equation for it. I'm talking about buoyant force. Okay. So for a submerged object, you have a buoyant force and you have a weight. And basically, if the buoyant force is bigger than the weight, the thing accelerates upwards. It's slowed down by water drag. If the thing has a bigger weight than a buoyant force, it accelerates downwards. It's slowed down by the buoyant force. And if the thing is in neutral buoyancy, it kind of stays where it is. If you're working on an oil rig and you have to go down under the water and you've got to tighten a bolt, the last thing you want is a wrench which has got just the density of metal, because if you let it go, it's going to fall to the bottom of the ocean. So they make tools with handles on so that the total density is the same as the density of water. Salt water, maybe fresh water, depending on what you're doing. And then if you let it go, it's not going to just stay perfectly in front of you, but it won't accelerate upwards, it won't accelerate downwards. It'll stay roughly where you are. Neutral buoyancy. And they just make it by making the handle, a certain density. Submerged object, the volume of the displaced fluid is equal to the volume of the object because it's submerged. I'm running out of time, so I'm going to stop there.